Okay, this then brings us to the last presentation of today's workshop, and I'm very happy to welcome Zaher Kassas here at our workshop, not only since he will deliver an excellent presentation about a look at the stars, LEO PNT with uncooperative satellites, but also since he is a very active supporter of IEEE LEO sats. He also helped in co-organizing this workshop here. So yeah, it's my pleasure to welcome him. And yeah, basically, Dr. Zaher Kassas, he is the TRC Endo Chair in Intelligent Transportation Systems and a professor in the Department of Electrical and Computer Engineering at The Ohio State University. He is the director of the U.S. Department of Transportation Center, Carmen, focusing on navigation resiliency and security of highly automated transportation systems. He started his academic career in 2014 at the University of California, Riverside, then was an associate professor at the University of California, Irvine. Then he was very early promoted to full professor and joined the Ohio State University in 2022. His research interests include navigation systems, low Earth orbit satellites, cognitive sensing, and software-defined radio, intelligent transportation systems, autonomous vehicles, and cyber-physical systems. And with this, it's my pleasure to hand over to you, Zach.
All right. Thank you very much, Marcus. Can you hear me? Can you see my screen?
Yes, we can see your screen and hear you very well.
Okay, excellent. Well, good afternoon, good morning, or good evening, or maybe good night for some of you. Thank you for your interest in this workshop. We had, as Marcus said, a very successful version in person in the IEEE YZ conference in Daytona Beach last December, and we thought, given the interest and timeliness of the topic, maybe we'll offer a virtual version, and I'm very happy to see the excitement around the topic. So I will close a series of very exciting and insightful questions from my esteemed colleagues. Basically, let's take a look at the stars and see what we can do with LEO satellites for PNT, specifically with satellites that are uncooperative. So first and foremost, I acknowledge my students, current and past, that contributed to many of the work that you are about to see here, besides, of course, other research projects that we have in my lab. But we've been talking a lot about LEO PNT, right? But why are we interested in it? The reason is it starts from medium Earth orbit, not low Earth orbit, which are GNSS satellites, which really got us spoiled by providing us with amazing PNT over the decades, right? From GPS, GLONASS, Galileo, Beidou, that touched every aspect of our modern day life. But because we got spoiled, whenever GNSS is unavailable, that started disrupting life as we know it. So that's why we need to consider friends for GNSS that are in low Earth orbit to continue with our daily lives. Obviously, our esteemed colleagues, specifically Eldar in the beginning, talked about, the navigation importance in everyday life. So what makes us interested in LEO satellites for PNT? Well, first, they are abundant. As you can see here, in 2019, there were about 2,200 satellites in LEO, whereas by 2029, they predict this number to dramatically increase. Some predict it to be 57,000, but I think it's going to be much higher than that. The signals are more powerful than GNSS, given the proximity of the satellites being in low Earth orbit compared to medium Earth orbit. The satellites are in diverse orbits. The orbits are faster, also considering their proximity. So now Doppler becomes informative. The different constellations transmit in different bands of the spectrum, so that also makes things more robust for interference. And if you exploit these signals opportunistically, pretty much the signals are free to use. So there are different schools of thought for LEO PNT that you can classify. The first is PNT dedicated LEO. So basically it says, let's launch LEO constellations into space and have them transmit a dedicated PNT signal. So similar to GNSS, if you will, but they are in low Earth orbit. There is dual purpose LEO. So we have a constellation that has some purpose, for example, transmitting communication signals or broadband connectivity or whatever purpose is, but now we also transmit a PNT signal simultaneously. And the last one, I would say, is the more sustainable from a space domain analysis, and from a spectrum analysis, which is a fully opportunistic LEO. So let's exploit what's already being transmitted from space for PNT purposes. Okay, and those are some references about different, I would say, papers and that had studied the different schools of thought. Some examples you can see in the PNT dedicated LEO in front of you. Trust Point, ESA is interested also in their own constellation, and so are other commercial, I would say like Zona. Dual purpose LEO, you have Iridium next and Global Star, and then fully opportunistic LEO, as you would expect, any constellation could fall under this umbrella. And this talk will focus on the third category. There are challenges, research challenges that one has to overcome if you are to exploit LEO satellites for PNT. The first being, well, the signals are mysterious. Satellites do not necessarily disclose publicly what signals they transmit. So you will have to come up with a solution. The most easy is reverse engineering, but I would say is not very robust. So maybe blind signal processing approaches or cognitive receiver design is more fruitful here. The unknown clocks, you don't necessarily know the timing and stability of the timing errors and stability of oscillators on board these satellites, so you will need to compensate for that. Atmospheric errors, now that we are dealing with different frequency bands as well, that becomes an issue. And finally, some of the attendees asked about large ephemeris error because the satellites do not disclose where they are precisely, similar to GNSS. You can rely on publicly available files, but you will have to resolve, the errors and uncertainties that grow over time, which could reach several kilometers. So I will touch a little bit on all of these challenges in this talk. I will start by talking about opportunistic positioning with Starlink LEO satellites, and I will take you back to the year 2021, and this is where my students and I revealed to the world that we can exploit the Starlink constellation for PNT and localized ourselves pretty accurately. This work got a lot of attention, appearing in Science, IEEE Spectrum, among of dozens of other media outlets. I will not go through the details because, this is more of an overview talk. Otherwise, each of the topics I will discuss will take me, several hours to just discuss in explicit details. But I'll give you pointers where you can go and find the necessary details. So this is a high-level block diagram of the carrier phase tracking approach that we came up with for the Starlink constellation. Those are the experimental results. We started with an initial estimate about 179 kilometers from where the receiver really was. Listened to 6 Starlink satellites as they flew overhead. You can see here the carrier phase error and the sigma bounds from our tracking loops. And we managed to localize ourselves, in 3D about 33.5 meters and 2D about 26 meters. And this is the paper, if you are interested, appearing in TAES in 2022 about how you can do this. Then we evolved our technique and we developed an approach based on match subspace detection theory. This work got featured on the cover of Inside GNSS, among other publications. And this is here the TAES technical paper that discusses this topic. Actually, it got a lot of interest from readers of TAES, was the most downloaded from July 2022 through January 2023. We later on in this paper here in the IEEE signal processing letters evolved the approach even further and reduced the computational complexity of this method and even applied it to other constellations, specifically the OneWeb constellation. But, this is, a very high-level overview of how it works. You have a sequence of binary hypothesis tests that you do. You null, the satellite, the most powerful satellite one at a time. You estimate its Doppler, and then, from there on, you start tracking the Doppler. This is the final result with the same data set as we studied earlier. We managed to get an improved positioning performance. You can see here the 3D error was about 23 meters, the 2D error was about 10 meters, with the same 6 Starlink satellites that we studied in the first paper. Then that led us to, evolve our thinking even further. And we thought, well, what if Starlink changes its code? What if Starlink changes its signal, right? So can we come up with something that is agnostic to the modulation and multiple access scheme adopted by Starlink constellation or pretty much any other constellation? Because, if Starlink is not the only constellation that is in space. There are other constellations that I will show you in this talk are extremely fruitful. So that led us to think of the idea of the beacon. And this is a pulsar, right? We are talking about space here, so might as well borrow something from space. And the beacon is a periodic sequence that is transmitted in virtually all communication signals or communication systems for synchronization purposes. Okay, some beacons are explicit, right? For example, if you look at GPS, the PRN, the pseudo-random noise code, is the beacon of GPS. Whereas in other communication signals, the beacon is implicit, right? So for example, in 5G terrestrial signals or 5G new radio, the beacon is an OFDM signal. We know this beacon because we can open the 3GPP protocol and we can get it. Whereas if you look at other constellations, NOAA, Orbcomm, Iridium, Starlink, OneWeb, they have a beacon, but they don't disclose it. So can we get this beacon in a cognitive way or in a blind way? Can we estimate it despite that it's not fully disclosed to the public? I'll not go through this, but this idea of the model beacon, we recently discussed it in complete details in this JSAC paper that was published last year. If you're interested, you can study it. It tells you what's the fundamental tracking performance and design considerations for, a generic radio navigation signal. And later on, we developed a cognitive software-defined radio that is capable of exploiting these satellites, in an agnostic way, regardless of their modulation multiple access scheme. So once again, I will not go through this. This is nearly half, if not more, of the PhD of one of my students, Sharbel Kozhaya. But this idea was first released in the IEEE ION Plans Conference in 2023. You are invited to take a look. And we are hoping in the next few months, the journal version of this work will be published that contains more details about the topic. But we put this into test. We managed to acquire and track OneWeb, Starlink, Iridium, Orbcomm, and NOAA with the same cognitive software-defined radio. You can see here the Doppler curves for these constellations and the Doppler error, right, in the receiver, which is, less than 10 hertz. And superimposed on what we are estimating for Doppler from this receiver is what we would predict to estimate from TLE and SGP4, right? So that tells us that whatever the receiver is outputting is actually meaningful. Then we put this, and if you're interested in more details, please check out this paper in ION GNSS 2023. Then we put this into test and we said, okay, can we place our initial estimate very, very far from where we really are. So we placed it 3,600 kilometers, which happens to be in the city of Irvine, California. And that's where, the original results that I showed you with Starlink were there. So we simply, didn't adjust the initial estimate of the filter. And then we said, okay, let's listen to 2 OneWebs, 1 Iridium, 1 NOAA, 4 Starlinks, and 1 Orbcomm, and see if we can estimate where we are. And we managed with a nonlinear least squares that fused the Doppler measurements through that cognitive receiver. We managed to estimate the position of the receiver to within about 5 meters. Okay, so that gives us confidence in the receiver itself. Later on, we started, using the receiver to study more the signals of different constellations and reveal, some salient properties for PNT. One such work appeared in TAES on the OneWeb constellation, which transmits in different beams and has, different sequences based on the satellite and so forth. If you are interested, this paper in TAES discusses the beacons, the beams, and, some positioning performance with the OneWeb constellation. But this here on the left, you see the output of the receiver listening to different OneWeb satellites that flew over us, in total 9. And you see here, this behavior here is due to the beam switching, this curvature, if you will, and the carrier to noise ratio. And we even explained it based on FCC filings. So it actually matches what one would expect as the OneWeb constellation switches its beam. You can see here how clean the Doppler tracking is. You can even estimate the code delay, or which is equivalent to the pseudo range. This is the carrier error, and this is the code error. Okay, so now let's look at positioning. So initial estimate 50 kilometers away. We listened to all of these OneWeb satellites, and this is the estimated position. And the reason you have more uncertainty in one direction versus another, it has to do with the way the OneWeb constellation organizes its satellites in orbit. So they all go north-south. This basically gives you more favorability in geometry in one direction versus the other. As I said, if you are interested, check out the TAS paper for all details. So then we went back to the Starlink constellation and we said, well, is there more that we can exploit from the signal? So we heard earlier about from Winfried's talk about the PSS and the SSS that was disclosed in the literature. But it turns out if you use this cognitive approach, which does not reverse engineer the signal, it allows you to basically reconstruct the entire OFDM beacon that Starlink transmits, or the entire OFDM frame. So if you see here, this is the PSS and SSS of the, and where it lives in the entire OFDM frame. And this is the entire beacon. This is the entire OFDM beacon that Starlink transmits. Okay, if you're interested to learn about this, and pretty much I would call it the manifesto of Starlink for PNT, then I will point you to the two papers that we recently published. But first, let me tell you why this should be of interest to the community, why this is very, very exciting. Well, first of all, using the full beacon will give you a much, much wider bandwidth to deal with, which gives you much better resolution in the time domain, right? So if you use the 240 megahertz bandwidth, you can see here how fine your autocorrelation function looks. So what you see here on the right is a zoom of what you see on the left. Of course, if you use a lower bandwidth signal, then you have a wider autocorrelation function. So essentially using the full beacon enables you to get nanosecond level precise code phase tracking. The other advantage you get is better resolution in Doppler. So if you use the PSS and SSS that was disclosed in the literature, this is your Doppler ambiguity function, right? If you use the full beacon, you see this very sharp peak, right? This is a zoom on it. So essentially what this tells us, using the full beacon will gives you Hertz level Doppler tracking. And finally, you will get an 18 dB boost in your carrier to noise ratio. Okay, so those are experimental results. This is if you track the PSS SSS, and this is if you are dealing with the full beacon. Okay. So if you are interested to learn about this, we recently published a paper called Unveiling Starlink for PNT in Navigation, which is the journal of the Institute of Navigation. There is also a webinar that's about 1 hour long that my student, Charbel, the first author on this paper, gave. Okay, so let's see now how well we can do in terms of positioning with the full beacon. So this here is a 600-second recording. This is here the number of tracked satellite at any point in time. This is the carrier to noise ratio. You can see here, we are getting close to 60 dB hertz. Theoretically, we showed you can even get above 70 dB hertz. This is the Doppler shift. You see clean Dopplers. This is what Winfried alluded to earlier about the code phase being choppy, using pseudo ranges from Starlink in a standalone fashion is not usable as of right now. You have to do a lot of massaging and stitching and maybe multiple receivers to deal with it. But Doppler is pretty helpful, right? But I will show you what you can do with Doppler alone. And you can see here, on average, you can see 3 Starlink satellites above us. And that's with very cheap hardware with a low noise block. Essentially, my students did an experiment more recently, a couple months ago, and they have noticed that the number increased by about 4 satellites. So you are getting, on average, about 5 Starlink satellites overhead. So this is random initial estimates, that spans pretty much the state of Ohio. for where we think we are. The green is where we really are. So we use the batch-weighted nonlinear least squares. We use the full beacon to give us the Doppler curves or the Doppler frequency, and then we estimated our position, and we used this formula here for our weighting, which is proportional to the carrier to noise ratio. So it turns out that if you wait for half a second, all of those estimates collapse to within a 90th percentile of 1 kilometer error. Okay, so if you wait a little longer, so if you wait for 5 seconds, then your 90th percentile is 22 meters. If you're a little more patient, within 10 seconds, then you're down to 4, and finally 20 seconds, you're down to 2 meters. Okay, and you can see here the CDF plots. If you're interested, check out the journal paper. It tells you everything you need. So to demonstrate why this 18 dB is very exciting, we decided to put it on a platform that is very, very limited in terms of payload. Okay, so to motivate what that platform is, we started thinking, well, you know, if you're standing still, we showed that you can get 2 meters in 20 seconds. And if you are standing still, right, you can afford a bigger payload, and that 18 dB may not be super necessary. Well, if you have a car, then the payload, you know, will get more limited, but we already have demonstrated ground vehicle results in this paper here in Ion GNSS. If you're interested, you can check it out. And we showed you can get, you know, about 4 meters in position root mean squared error. Well, how about if you put it on a UAV? Well, it turns out that we had done UAV flights back in 2018, and, you know, I don't think it's super exciting anymore. Well, okay, so if not a UAV, then what? Well, how about urban air mobility? Also, you will have a limited payload, but, you know, we don't have access to those flying taxis. How about going, you know, to Mount Everest, where, of course, you are now strapped with some hardware and you can't carry, you know, a big dish with you? Well, you know, we didn't want to go to Mount Everest. I think it's not super feasible. How about commercial cruising commercial plane cruising altitudes? Well, also we don't have access to those at the time being, nor we have access to the Blackbird cruising altitude, which is even higher. So that led us to call this experiment Icarus, which is named after a Greek mythology for someone who was trying to escape from the island of Crete by flying, you know, and then his father warned him, don't fly too high, otherwise your wings will burn and you will fall to your death. So we called this Icarus. And the idea is we want to fly very close. We have limited payload. And if Icarus wants to fly, he cannot carry this big dish. So probably you had guessed what we really wanted to fly is a high altitude balloon. And you see here, the goal was to go over 25 kilometers above ground. We were constrained to a payload of less than 12 pounds. And this work appeared in the IEEE WISE conference, where we had the LEO PNT workshop that inspired this virtual workshop that we have here. So let me play you a quick video of the Icarus experiment. So this is Will Barrett, my student that led the development of the payload. You know, it was a year-long effort by several undergraduate students that did a fantastic job designing the payload that could sustain this very, very high altitude. We ended up sending it to New Mexico. And this is here the launch date. I'll just skip through some you know, videos for the sake of time. Ultimately, we launched the balloon. It traveled for 105 kilometers, and it reached a peak altitude of about 83,000 feet above ground. This is the balloon retrieval. You can see here there was a lot of turbulence along the, you know, at this very high altitude. But ultimately, what we managed to show is you can use Starlink signals at such an extreme environment and navigate the balloon, you know, relatively accurately. So how accurately? Well, the overall trajectory was nearly a kilometer in 50 seconds, and our position root mean squared error was about 12.3 meters using Starlink signals alone and some altimeter data. We later on evolved this work and included OneWeb signals. So if you are interested, you can check out a paper that we just presented last week in the IEEE ION Plans conference. So how do we deal with ephemeris errors, right? So this is a question that was raised. I will try to fly through the next slides because we are starting to run out of time, but I will give you good pointers to find research questions. The first approach we developed back in the year 2018 was called STAN, simultaneous tracking and navigation. And we continued to evolve this idea until we published it as a full tutorial that has explicit details that appeared in the IEEE Aerospace Electronic Systems magazine in 2024. The idea is you can simultaneously track the satellite, refine its ephemeris, and navigate with its signals. Okay? Then we evolved this into differential STAN. So those are some media that covered this work. But essentially, what are we talking about? So what a lot of the community does today is to use SGP4 software to propagate, some initial estimate that you may get from, let's say, TLE files. STAN tells you, you know what? I'm not going to trust the ephemeris of LEO satellites. Instead, I'm going to estimate them in my state vector. Differential, basically, if you're familiar with somehow my screen paused. Okay, differential, if you're familiar with the differential GNSS or differential GPS, tells you, well, I'm going to set up a base and it has its knowledge of its own position, let's say, or of its own states, and it will communicate with the rover that doesn't know where it is, some differential corrections. In this case, the rover only estimates its states. Okay, and finally, the differential STAN, if you wish, is a fusion of STAN and differential SGP4 LEO. If you're interested in all of these frameworks, I will point you to, if you bear with me, to this paper that will appear in the AES magazine. It's actually already in early access. You can check it out, but it will discuss the results I will show you later. So basically, it shows you this block diagram, what's open, what's closed, what gets estimated, what are the LEO satellite dynamics, what's the IMU model dynamics that you can equip your vehicle with, measurement model, whether you have a pseudo range or a pseudo range rate, which is equivalent to Doppler, clock dynamics model, and so forth. To show the power of the different techniques, we set up a simulation where a vehicle navigated, an aerial vehicle navigated along this trajectory. We assumed it a fixed wing UAV, 28 kilometers and 300 seconds. It had an altimeter, a tactical grade IMU, and an OCXO, an oven-controlled crystal oscillator. We simulated a Globalstar, Starlink, Iridium, OneWeb, and Orbcomm constellations. We used it for their ground truth, the HPOP, and then we tested out pseudo-range versus Doppler measurements. So let me play you this video showing you the aircraft flying. The SGP4 LEO very quickly diverges. So that's a cautionary tale not to use, such erroneous ephemerides when you navigate. Then you see here the STAN, differential STAN, and the differential SGP4 LEO. So let's look at the performance with pseudo-range alone versus Doppler alone. And I'm going to calculate the 3D position RMSE with STAN, differential SGP4 LEO, and DSTAN. I'm not going to show the SGP4 alone because the errors are just humongous. So if you use the older constellation, Orbcomm, Iridium, and Globalstar. So in this case, over the UAV, there was 1 Orbcomm, 2 Iridiums, and 3 Globalstars. This is what you get. STAN, 15 meters, and then differential SGP4 LEO, interestingly enough, was able to compensate for a lot of the ephemeris errors and even timing errors in the satellite, and DSTAN was better. Okay, even, what's interesting is differential SGP4 was more powerful than STAN. And this here you see the Doppler, which is slightly worse than if you have access to pseudo range. Well, if you use the OneWeb constellation, it turns out that there were 22 satellites, coming in and out while the UAV was flying. This is what you get. If you use Starlink, it happens that Starlink had more satellites than OneWeb. So to be fair to OneWeb, we only selected 22 of the Starlink constellation. This is what you get. However, if you get greedy and you say, you know what, Starlink has more satellites, I'm going to use them all, it turns out that the differential SGP4 will be unable to compensate for the large number of ephemeris errors. Okay, and model mismatch. And this has to do with how the errors end up getting mapped from the satellite states or the state space of the satellite to the measurement space, and then finally to the estimate space of the receiver or the UAV. And then if you use them all, this is what you get. Then we put this on a ground vehicle, and we did the same, but with experimental results. I will show you real quick. The base was about 1.2 kilometers from the rover, which was, as I said, a ground vehicle, and we see something very similar. GNSS, INS, after GNSS cutoff is pretty bad. That's to be expected. SGP4 LEO, 41.29 meters. So STAN, better. Differential is better than STAN, and D-STAN is the best. And here we didn't see, the behavior of explosion in differential SGP4 LEO because we did not have as many satellites. Read the paper if you're interested. It has very, very interesting insight about what you should and shouldn't do. I will really skip through this very quickly. I will just show you some recent work that we had done very rigorously to study the errors in the satellite ephemeris and timing errors. This is a series of papers that we had published that helps you disambiguate the spatiotemporal errors. I would pinpoint the last paper because it does have a full-blown analysis of modeling and compensation of timing and spatial ephemeris errors of non-cooperative LEO with application to PNT. And this is what it allows you to achieve. Meter level accuracy after having access to GNSS for about 30 seconds. Okay, from that point onwards, we traveled for 40 seconds with LEO satellites that are non-cooperative, but during those 30 seconds, we managed to correct for their ephemeris and timing errors. And then we evolved this work later. And actually, we presented it last week at the Plans conference. So be on the lookout for this paper because it gives you more of a warm start approach to navigating with non-cooperative LEO. Another very nice work that was done by one of my students is to enable you to do these differential corrections from very, very, very far away. And I will just skip through the details. I'll simply show you, check out this paper in TAS. It will really tell you how to do ephemeris and timing error disambiguation, enabling precisely your PNT. I'll skip through the details for the sake of time, but the idea is, there is a unique point in time where the ephemeris and timing errors get decoupled. You can estimate them. You can then transmit them to an unknown rover from a reference receiver that's very, very far away. And if you wonder, well, how far away? I can tell you we've extended the baseline for hundreds of kilometers. So these are experimental results that we had set up a reference receiver in the city of St. Louis, Missouri, 635 kilometers from where we are. We did the ephemeris and timing correction, communicated them to the unknown receiver in Columbus, Ohio, and managed to get to meter level accuracy. Okay, so starting from an initial estimate 200 kilometers away, if you use the uncorrected ephemeris, you are down to 2.41 kilometers. Well, obviously that's not great level of precision, but if you use the corrected ephemerides that were transmitted 600 kilometers away, then you can get down to an estimate about 8.78 meters. I think I will stop here because we are running out of time, and I will accept any questions from the audience.
Hey, thank you, Zach, with this impressive overview on the tremendous things you did in the area of Starlink opportunistic navigation. And we received a couple of questions. So let's see. The first question was, there was a question regarding the satellite identification problem. So when we receive a signal from LEO satellites, one method to know the actual transmitter is decoding the received signal. Is it possible to identify the transmitter from a dense LEO constellation, for example, Starlink, without decoding the signal?
That's an excellent question. And coincidentally, last week, one of my students, Jennifer Sanderson, presented in the Plans conference, I would say the first ever work that, to our knowledge, that addresses this. So this is not, I would say, if you abstract the problem enough, this is a data association problem that has been studied over the years a lot in the radar community. So we had adapted some of the classical techniques to the LEO PNT problem, and she presented some really nice work that shows how you can do data association. The fun part about this problem is you have uncertain LEO ephemerides, right? So she took that into consideration because if you are using TLE and SGP4, you don't know exactly where the satellite is. And then you are interested to localize yourself, right? So you may not know exactly where you are. So she started even introducing uncertainty in your own position. And she showed that you can get to about 100 kilometers of uncertainty before the data association start mismatching satellites. As I said, we started thinking about it. This is the beginning of I would say, hopefully some fruitful studies in the field, but check out the IEEE/ION Position, Location, and Navigation Symposium proceedings. The paper is by Jennifer Sanderson and myself, and you can find hopefully some answers that will quench your thirst.
Okay, thank you. Okay, and since we have to close that workshop in time, we have one or two additional questions which we will forward to you. Then we can answer it via the website or directly. So thanks again, Zach, for your excellent contribution, not only with your presentation, but also as a co-organizer of that workshop. You really are a great help in organizing such things. Yeah, with this, we are at the end of today's workshop. I hope that all of you enjoyed the workshop. I personally really did enjoy it very well. We exchanged different aspects and views on LEO PNT. Of course, I want to thank all the speakers again, because we from LEO Sats, of course, we are just the organizers, but you are the ones who deliver this outstanding and excellent content. So we are looking forward to more events, and maybe also together with SAC organizing future in-person events on the topic. And with this, yeah, have a good evening, a good rest of the day, or a good afternoon. Thank you.
Thank you, Marcus.
Okay.
Thank you, everyone.
Thank you.
Bye-bye, everyone.